Mathematical models were also used in the biological field, in particular in the evolution of epidemics. The model that we are going to see is a model proposed by Kermack and McKendrick in 1927. Kermack and McKendrick consider the total population to be equal to n, some number n, so this is the total population, and this total population is divided up into three subparts. The first subpart is given by the number of susceptible subjects, and this is indicated with the letter S. S represents the number of susceptible subjects, which are healthy people that can become ill. Then we have the number I of infectious people, or subjects if you want. These were susceptible people that became ill. And then we have the number of removed, which are subjects that go out of the illness cycle. These are removed people or subjects. These removed can either be hospitalized people or dead, or people who have just overcome the illness. There are several hypotheses that the model employs. I will mention all of them. So the hypotheses are the following. So the first one is that n is a constant, which means that we are going to neglect births and deaths, or even immigration or emigration, which is something reasonable for quite short periods of time. So we basically mean that the sum of the susceptible subjects with the infectious people, with these removed people, this is equal to a constant. So we also know that this sum here is a constant, because s plus I plus r gives me n. Then another hypothesis is that all subjects who become removed after being infectious develop immunity, which means that susceptible people can become ill just once, not more than once. So for example, this is not the case for those illnesses such as influenza or the cold, where you can get it multiple times. And the model can be adjusted in that case, but I will not discuss it here. And then there is no time lag, which means that as soon as a susceptible comes into contact with an infectious, he or she will get ill instantaneously and with just direct contact. I can put it here, instantaneous transmission. And then the number of susceptible and the number of infectious move randomly in the environment, whereas the removed do not move because, of course, they can be either dead or hospitalized people do not move, and therefore the removed subjects are a little different than the susceptible and the infectious. And we are more concerned with the susceptibles and the infectious people. And another hypothesis is that n is large, which means that we can neglect genetic differences, for example. So we can consider all these quantities to be average values that can vary over time, because otherwise we would have genetic differences to be considered in susceptible subjects or infectious people, and that's of course something that would complicate the model, and we don't want to do it here. So the cycle is something like this. We have susceptible people or susceptible subjects that can become infectious people, and then the infectious will become at some point removed people. And once you become removed, you don't go back to being a susceptible. You just remain removed, and therefore you will not become ill again. So this is a hypothesis, but the model can be adjusted in such a way that, for example, removed subjects can become susceptible again. I'm not considering it here. What we have to do now is we have to construct our equations of the model. So we have to find, for example, the rate of change of the susceptible, ds over dt. How does the number of susceptible change over time? Well, we know that the susceptible can encounter infectious people, and when they encounter infectious people, they will become infectious. So here I will have to put a minus sign and then some constant, and I will put a product of s times I, because this product here is proportional to the number of encounters. And here I have to associate this equation with the initial condition s of 0 equal to some s sub 0. Something like this. K is an important constant because it is related to the disease, to how fast the disease will spread. In particular, it is also called the transmissibility coefficient. It tells us how fast this disease can propagate through the population. It has to do with the disease, not with hospitalization, healthcare, or something like that. And then we have to find the rate of change of the infectious people, di over dt, which will increase when there is an encounter between susceptible and infectious. So here I will put this same quantity here with a plus sign. So I will have plus k times si, because when there is an encounter between a susceptible and an infectious, the susceptible will become infectious, and therefore it will increase the number of infectious. So di over dt will increase due to this effect. but I will also put a minus sign, some constant that I will call lowercase h times I. So let's talk about this term here. In particular, this constant h depends on the healthcare system of the country where the population lives. And in particular, I'm hypothesizing that the more infectious people there are, the more people will be removed because of the healthcare system. So this is kind of intuitive to hypothesize, because if there's many infectious people, the healthcare system will take care of them, and therefore more of them in proportion will be removed. And therefore this quantity, the I over dt, will decrease the more infectious people there are. And therefore it would be optimal to increase this h as much as possible. So this can be adjusted if, for example, you boost the healthcare system, if you improve it. This parameter can be worked on. That's why this model is very useful, because it can also tell us how we can interfere with the illness, how we can intervene by changing this h. And then finally we have to find the rate of change of the removed over time. And this is quite simple to do, and we can also do it by using one of the assumptions. In particular, we know that the total number of people with respect to time will not change. So the derivative of n with respect to time will be equal to 0, because n does not change. Therefore, since n is the sum of s, I, and r, this means that this is the derivative with respect to time of s plus I plus r. And this should be equal to 0. But the derivative is a linear operator, so we can also rewrite it as ds over dt plus di over dt plus dr over dt equal to 0. Now here we already know how to write these first two terms, this one, ds over dt, and this one, di over dt. So I can substitute these two equations here into this one, and I can find dr over dt. Okay, so dr over dt will be equal to minus ds over dt minus di over dt, and I can substitute this expression for ds over dt, so I will have minus with another minus sign will become a plus, so I have k si, and then I have minus di over dt, which is minus k si plus hi. So here these two terms will cancel, and I will be left with hi equal to dr over dt. So I can replace it here, and so this will become dr over dt is h times I. So the more infectious people, the more of them will become removed, which is something intuitive. So this term here, hi, will increase the number of removed. And we have our model here, which consists of three equations, not just two, as the prey-predator model. But we are actually interested in the behavior of infectious people and susceptible people here. So I will focus on the susceptible and the infectious. Therefore, I will consider just these two equations for now, which, if you take a look at the model, does not contain r, so there is no r here. And this means that I can consider the first two equations independently of the third one. So I can first solve the first two equations, and then I can solve the third one, because the third one, of course, should be solved afterwards, because I have to find the number of infectious here in order to solve this one. So first I have to solve the first two, and then this last one. But I will focus on the first two there, because that's what we want to do. And we will use Scilab to model these two equations. We already know how to model these two equations. If you take a look at the terms very carefully, you can see that this is exactly the prey-predator model, with one of the constants equal to 0. So the first equation, ds over dt equal to minus k si, should remind us of the number of prey. So I have dx over dt equal to some constant that I can call k1 times x, and then I have minus k2 times x times y. So in this case, if you compare this equation with that equation there, you can find that k1 should be set equal to 0, and k2 is equal to k. S is equal to x, okay, and therefore here we find exactly that equation if we also set y equal to I. And then I have dy over dt, which is di over dt, equal to some constant k3 with a minus sign y, and in this case k3 will be equal to lowercase h here. And then I have plus k4, which is equal to k times xy, which is exactly our model above. Okay, so we can use what we already know from the prey-predator model in order to model the behavior of susceptible and infectious people. Before using Scilab, which is quite straightforward in this case because I simply have to use the same model that we used for the prey-predator model, the pure prey-predator model. I want to discuss something more. In particular, I want to say something more here on the behavior of infectious people and susceptible people. So I am focused on the plot S and I. What I want to show is that the curves that we can find in this plot are of this form. So I can start from this point here, which is the point S0 by 0. This is the initial condition. And then, depending on where I start, the plot can be like this. At first, the number of susceptible decreases and the number of infectious people increases. And then I will go down and this will decrease like this. So there is a maximum here on this curve, and this maximum occurs at the point S equal to H divided by K. So we can show this also mathematically. This is quite easy, so I can do it in a few steps. This also means that if the starting value for the susceptible is less than H over K, so if this happens, we start here in this region. Therefore, the curve will decrease right from the start, because if S is less than H over K, the curve decreases. So it means that there is no epidemic. If this happens, it means no epidemic. Whereas if S0 is greater than H over K, we have an epidemic because we start somewhere here in this region. Okay, so you can see that there is an increase before the subsequent decrease. This is the epidemic zone. How can we show that there is a maximum here in this curve and it is exactly equal to H over K? This is quite simple because what we have to find is we have to find the rate of change of the function I with respect to S. And we have to set it equal to 0 because it means that here we have a curve I that depends on the variable S, and the slope at the maximum will be equal to 0. So we have to set the derivative equal to 0. And now how can I find di over ds? Well, I can also rewrite it like this. I have di over dt divided by ds over dt. So I have just simply multiplied both of these differentials by 1 over dt, okay, which is not very formal, but this can be done. And I can use the equations that I have, because di over dt is just ksi minus hi, whereas ds over dt is just minus ksi. This is just equal to minus 1 plus h divided by ks, because I can simplify I in the second term, and the first term is ksi divided by minus ksi, which is minus 1. And this should be set equal to 0, which implies that the maximum is found at s equal to h divided by k, as I said earlier. Now let's try to find this using Scilab. So let me open Scilab here. I will type xcos, and I will open the prey-predator pure model here. This is the model that we built together. And what I have to do is I want to change some of these values because the model is already there. It's already prepared. So if you recall, in this loop here, there was the variable x, the number of prey. But in this case, the number of prey is the number of susceptible. So here I have the equation of susceptible subjects. First, let me save it as the epidemic model. Here I will change this constant to the value 0. Now this constant can be left as it is, whereas down here I have the variable y, which represents the number of infectious. This constant minus 1.2 is minus h, whereas this constant here should be equal to k, which is equal to 0.01. So let me put it equal to 0.01 with a plus here, not with a minus, because here I have plus k times si. And now let's try to first calculate where the maximum of the curve would appear. The maximum is equal to h divided by k. So h in this case is 1.2 and k is 0.01. So it means that the maximum is at 120. So s should be greater than 120 if we want to see the maximum. So this is the starting point for s. We have to open this integral block and set the initial state to a value that's greater than 120. So you will choose 150, for example. Now let me also take a look at the initial value for the infectious people, which is 18, and that's okay. And now what I can do is just start a simulation. Let's see what happens. Let's take a look at this XY plot, which is the SI plane. Let me enlarge this portion of the graph. And you can see here that there is indeed a maximum at about 120, and we start at 150. So the first portion of this graph, which starts at S equal to 150 and Y equal to 18, which is the number of infectious here. At first, we have that the infectious people start to increase, and consequently the number of susceptible will decrease. And after I reach the point where S is equal to 120, I will go down. So it means that the epidemic will have dampened. And you can see that even when we reach at some point a number of infectious people equal to 0, we have a non-zero number of susceptible people, which means that not all susceptible will become ill. So not all of them will get the disease, which is something that was not trivial.